Welcome everyone to lesson 26 for Education for Nepal English group. Here's our YouTube channel link. You feel free to click on it to watch past lessons in your free time. The first icebreaker for today is, what is your favorite quote, saying, or popular phrase? Or like, does anyone know any like famous English quotes? So we have an answer, and it seems to Neil Armstrong. Like, do you remember what his exact quote was, or because like he's probably said multiple things? Leo, how about you? What's your favorite quote?
That's a really good question right there.
Yeah, it
I
is.
mean, I have
And
to
I want you
say,
to answer it.
I was really inspired by I Have a Dream, man. Like, you know what I mean? Like that's just
Oh yeah, I feel you. I
inspiring.
feel you.
Thanks, man.
Okay, today we'll first start off with chemistry, and then we'll do history, and then we'll end off with physics. So in chemistry, we'll be doing entropy today, and also some like more thermodynamics, I guess. Okay, so last time we did chemistry, we did enthalpy. This time it's slightly different, something called entropy. So entropy is a measure of particle randomness or disorder. So yeah, this is like one of those really weird like measurement things because like you don't really you can have sort of a value, but like realistically, when you learn chemistry, no one really cares about the specific value of entropy. But we'll see the uses for entropy later. So entropy is represented by S, the letter S, and then here's an equation that you probably will never need to use, but if you would like to know it, here it is. It's just the Boltzmann constant times the natural log of the number of microscopic configurations. Like it doesn't even mean that much, honestly. Okay, so realistically, you don't care about the specific value of entropy. You just care about uh, what object has a greater, like which objects have greater entropy and which ones have like a smaller entropy. So as you can see from the image on the bottom, gases have larger entropies than liquids, and liquids have larger entropies than solids. That's because gases are obviously more random. You have like a bunch of little particles flying around um, when you have a gas, right? Like you give a balloon, the air inside the balloon is just a bunch of particles flying around. It's like really random. But if you have like a brick or something and it's just like solid, it's just like completely still, all the particles are like locked in and they're not moving. So you don't have any randomness. So therefore the entropy would be really low. So spontaneous. So there's actually two different terms we have here. So a reaction is spontaneous or thermodynamically favored if the reaction favors the formation of products. So like a fire is thermodynamically favored because once you light a piece of paper or like wood on fire, it's gonna keep burning until like the paper or the wood is completely burned up. Like you don't have to keep supplying energy in order for the fire to burn. The fire will just burn without anyone supplying like external energy. So you're like, if you look at the reaction, you're like taking in like the fire's taking oxygen and like I guess the paper wood or whatever, and then it's making carbon dioxide, right? So the reaction in the reaction, the products would be like carbon dioxide, and it's like the reaction is making that carbon dioxide without like an external supply of energy. And then for reversible reactions, basically a reaction where you can like reverse it. Like obviously, you burn something, you can't reverse it. Like you burn a piece of paper, you can't turn the ashes back into paper. But for reactions that are reversible, one way will always be thermodynamically favored or like spontaneous, and the other way will always be non-spontaneous. So basically, if one way works without energy, the other way has to have energy to work. Yeah. And then whether a reaction is spontaneous or not depends on the enthalpy and the entropy of the reaction. So here's like a chart that is pretty useful. So here you have entropy on top and then enthalpy on the side. So you have delta S, which is entropy, and then delta H, which is enthalpy. And you can tell that the reaction is spontaneous or like thermodynamically favored when delta S is positive and delta H is negative. Now I'll explain why this is later, but for now you just look at the chart and you can see that there's like only 4 possible scenarios. And one of them is where the reaction is always spontaneous, where the reaction is always not spontaneous, and then 2 where like the reaction's thermodynamic favorability depends on the temperature. Okay, now this is because we have something called Gibbs free energy. So free energy is energy that can be used to do work. It is represented with the letter G, and that's because it's like in honor of some American scientist named Josiah Gibbs. So this is now here's a useful like equation that you'll probably have to memorize for the future. The change in Gibbs free energy equals the change in enthalpy minus the temperature times the change in entropy. So basically, you can now see why the thermodynamic favorability of a reaction depends on enthalpy and entropy. So yeah, a reaction is spontaneous or thermodynamically favored if the change in Gibbs free energy, basically if delta G is negative. So here's like a way better chart. So you can see that delta G is always negative when delta S is positive and delta H is negative. And this is because if you go back to the previous, like on this slide, if delta H is negative and delta S is positive, you have a negative number subtracting of a positive number, right? So you'll always end up with a negative delta G, like no matter what the values are. So like a reaction would always be thermodynamically favored because you would always have a negative delta G. Delta denotes change. So delta just means like a change. Yeah. So if you have one value and then you have another value, delta just means the change in these two values. So like if your H was 1 initially and then it became 10, your delta H would be 9 because it's 10 minus 1. And so yeah, this chart is pretty important to note because it can easily help you find out whether a reaction is spontaneous or non-spontaneous, because you would instantly look at the signs of delta H and delta S and then be able to tell whether the reaction is spontaneous or not. Okay, yeah, whoever's making noises or like Gracia, can you mute them? So the first question is, if a block of ice melts, is the change in entropy positive or negative? So basically, is delta S increasing or decreasing if a block of ice melts? Okay, someone type positive in the chat. That's correct. Although I would encourage you to unmute your mic and say it out loud. So answers in the chat are great. I'm not discouraging it, but I'm just saying it would be better if you guys can unmute your mics and say it out loud. Okay, second question. And if you know the answer, please unmute and say the answer out loud. Or if you really don't want to, I guess you can still type it in the chat. When is a reaction thermodynamically favored in terms of Gibbs free energy? So what sign does Gibbs free energy have to be? What sign does delta G have to be in order for the reaction to be spontaneous or thermodynamically favored? If anyone knows the answer, please volunteer and unmute your mic and say the answer out loud. I see some people are typing positive in the chat. No, that is actually not correct. If you look on this slide, it stated that a reaction is only spontaneous if the delta G is negative. Okay, last question. Under what circumstance is a reaction always thermodynamically favored? So when will delta G always be negative? Does anyone know the answer? Come on, guys. When will delta G always be negative? When entropy increases. Yeah, you got half the answer correct. It's when entropy increases and enthalpy decreases. Both of these must happen in order for delta G to be guaranteed negative. Okay, now we're moving on to history. And I believe they're doing World War II.
They will be covering World War I. All right, so the cause of World War I was the assassination of Archduke Ferdinand, who was going to be like the heir to Austria-Hungary by a Serbian nationalist Gavrilo Princip. And because Austria, Hungary, and Serbia each have their own alliances, I, if one declares war on another, it'll cause a lot of other countries to get involved too. So Austria-Hungary like sent something to Serbia, but
An ultimatum or something like that, right? It's like call it ultimatum something.
yeah, the demands were just impossible to do, so they ended up declaring war on one another. And the alliance, so Austria-Hungary had Germany backing them and Italy, while Serbia had in the Triple Alliance, the Ottoman Empire is there too, but they'll come in later. And Serbia had Great Britain, Russia. So fighting World War I. So Germany at first followed the I'm not sad this S plan, where Germany would invade France through Belgium in the west and confront Russia in the east. So they basically tried to fight two places at once. In the Western Front against France, which they planned for it to be a quick victory, but it ended up turning into a trench warfare and lasting more than 3 years, which kind of ruined their plan. And then in Russia, it's really complicated, but they were eventually repelled, making basically just completely foiling their Schleifen plan. And then in 1917, 1 year before the war ended, I think, Russia pulled out of World War I because they were having their little communist revolution. All right. So America was at first neutral, following the no, they were not. They were ruled by a czar, so like an emperor kind of. They were not communist. They were Soviet. All right. America was at first neutral, remained on the sidelines. The Ottoman Empire joined the Central Powers near the beginning, so Germany, Serbia. And then the German U-boat submarines showed aggression towards neutral ships of the ships of neutral countries, including US ones. They sunk a lot, but the one that like convinced America was the Lusitania, which was a British ship that was going from like Pennsylvania to New York or something. I don't really know, which had US citizens on it. And that basically convinced the United States to declare war against Germany only. So after a few battles, the British won naval superiority in the North Sea, which forced Germany to. So basically, the Allies had naval superiority, and the Allies were producing 5 times more planes than the Central Powers. So they also basically had air dominance. All right, so World War One. Well, at the time they didn't call it World War One. Obviously, they couldn't predict World War Two, but it was called World War One because it was the first war of this large of a scale. And another reason that I read up was because it was the first like modern war. So the Spanish flu first killed a lot of people, actually killed more than the actual like guns themselves. It killed anywhere from 20 to 50 million people. And then some new technologies that were like widespread during this time were machine guns, like the one you see to the right, the middle picture, tanks, aerial combat with planes, and also radio. This war also introduced chemical weapons such as mustard gas, which would often backfire on the people using them as the wind changes direction. But chemical weapons are later banned by the Geneva Convention. Um, was weapon used in World War One? Like, do you mean like what weapons were used? I don't really understand the question. But if you're asking nuclear, no,
No, nuclear wasn't
that
invented
was
yet.
World War II. Well, we'll get to that next week. So the end of World War One. So the Central Powers lost. The Ottoman Empire or the Triple Alliance lost. The Ottoman Empire was weakened due to a nationalist, not national, just an Arab revolt that destroyed its economy. Austria-Hungary was slowly dissolving into two separate countries because of nationalist movements. And Germany's resources were overall dwindling, and its population's morale was low because their allies just all kind of surrendered. And this all ended in the Treaty of Versailles. The four people who were making most of the decisions were US, Great Britain, France, and Italy. None of the Triple Alliance countries had any input in the decisions made. And also Russia they weren't part of it either. The Treaty of Versailles basically pinned all the blame of World War One on Germany, forcing them to pay massive reparations, which was really problematic for them because they already had to like kind of rebuild themselves. And they had to give up, I think they said 10% of its 10% of their land, as well as all overseas possessions. And they also heavily restricted its military, like the size of the military. The Germany obviously hated this, and it would eventually lead to World War II. All right, so some questions. So the first two are who are the core members of the Triple Entente? And who are the core members of the Triple Alliance? Both on the same slide.
Germany, Austria, Hungary, and Italy.
All right, thank you. Does anyone know what about the triple? I think you answered Triple Alliance. What about the Triple Entente?
Great Britain, Russia, and France.
All right, that's correct. Thank you, Bishop. All right, name some. You don't have to name all. Just name a few of the new technologies that were used in World War.
Tanks,
Yeah, tanks were one.
Aerial combat,
Yeah.
machine guns,
All right. Yep, they're all
and
correct.
radio communication.
All right. Does anyone know why the United States joined World War One? The top right picture basically answers it.
Okay, I just want to say technically you're a bit wrong there. Like the Lusitania didn't convince the United States to join the war. It was the Zimmerman telegram.
Oh yeah, they sent to Mexico. Yeah.
Yeah, that's what officially made them join the war.
Yeah, there was a lot of things. Okay, so the Zimmerman telegram was this.
It's what like sparked them to join the war. But like before that, there's already like it's like this built up tension. But like
Yeah.
the Zimmerman telegram is what pushed them over the edge.
Okay, so the Zimmerman telegram was this encoded German message to Mexico, which is right below the United States. basically telling them to like not fight the United States, but kind of block our efforts to or impede us from joining the war. And we intercepted it, decoded it, and we yeah, we're kind of mad at Germany for doing that. All right, so let's go on to the last question. Who did the Allies pin all the blame on for World War One?
Germany.
Thank you, Michelle. That is correct. All right, we move on to physics.
And this is our last topic, and we'll be doing centripetal force. You have a question? What's your question?
Have any countries from Asia involved in the World War One?
I don't think
World
there
War
are.
One. No, in World War One, the only country that was really involved was Japan, but even Japan had really limited involvement. Asia became a lot more involved in World War Two, which happened 20 years later after World War One. But World War One was mostly fought in Europe. Okay, if there aren't any more questions, we're going on to physics. Leo.
Wait, do you want me to teach the entire thing? What?
No,
Okay,
you go over the
whatever.
lesson slides.
All right, cool. So yeah, so today's topic is gonna be about centripetal motion. So centripetal force is a net force that acts on an object to keep it moving along a circular path. So as you can see, we have the equation here. F equals mv squared over r, where F is the centripetal force, and then m is mass, v is velocity, and r is radius. And then on the diagram at the right, you can kind of see how it works out. Okay, and then we also have centripetal force and acceleration. So centripetal force is always pointing on to the center of the circle, and centripetal acceleration can be derived from centripetal force using F equals ma. Yeah, so after doing that derivation, we can get that the centripetal acceleration equals v squared over r. Yeah, where v is velocity, r is radius. It is also possible to find centripetal force using time and angular velocity. So here, as you can see, we have linear velocity equals to angular velocity multiplied by the radius. And then we also have the angular acceleration equals to v squared over r. And angular velocity
No,
equals
that's
to
regular acceleration, bro.
no angular acceleration. No,
Oh, no, never mind. Wait, no. Is that
yeah, no,
angular or regular?
that's angular.
Uh,
And then we have angular velocity, which is 2 pi over the time. So yeah, so angular velocity measures how fast it can go around the circle, where like 2 pi is 1 revolution. And then yeah, so using those we can plug into the equation, and then we can get the equation of F the centripetal force equals mass multiplied by radius multiplied by 2 pi over time squared.
okay, so the first problem is you have a 10-kilogram mass that's attached to a string and has a breaking strength of 200 newtons. If the mass is rolled on a frictionless surface in a horizontal circle of radius 80 centimeters, what is the max speed it can have? So if you were swinging a 10-kilogram ball on a frictionless surface, what is the max speed it can have if you can't swing it any harder than 200 newtons? Take a moment to answer this question, and then once you have the answer, you can say it out loud or type it in the chat.
Forty.
40 is close. 5,000 is a bit far. Here's a clue. Try changing 80 centimeters into meters and then recalculating your answer. So you guys, yeah, just turn centimeters, 80 centimeters into meters, and then try recalculating.
$400.
'I'll just give another hint. It's a really small number because remember you're taking the square root. So if it was 400, you'd be having a really large number before the square root.
Maybe 5.
5 is so close. Okay. No, you all, I know why you guys are all getting really big numbers. It's because, like I said, turn the 80 centimeters into meters, and then you'll have the correct answer. Like a lot of you guys that didn't turn the 80 centimeters
40
into
meters per second.
Oh, Bishal got the right answer. Yeah, the correct answer is 4. Okay, nice tries for all y'all, but yeah, because I told you guys to turn 80 centimeters into 0.8 meters. So here's the solution. Yeah, a lot of you guys are getting 40. I think this is because you guys didn't turn the centimeters into meters. But yeah, you guys are all really close, but only Bishal got it correct. So good job. So if you look at this, we can see that we can take the force, which is 200 times 0.8, which is the radius in meters, right? Because it's 0.8 meters equals 160. Then if we take 160 divided by the mass, which is 10, we get 16. And then as you can see, square root 16 is 4. So yeah, a lot of you guys didn't turn the centimeters into meters, so you guys ended up taking the square root of 1600 or like 1600, which ended up giving you guys 40. So if you guys just turned centimeters into meters, you would have all gotten the right answer. Okay, so the second problem is a ball of mass 5 kilograms is attached to a string of 50 centimeters. If the ball makes one rotation in 5 seconds, basically it can swing a full circle in 5 seconds. How much centripetal force does it have? So same thing here. Don't forget to change centimeters to meters, because usually when we do physics problems, especially when it's related to force, it's always in terms of meters and not centimeters. So yeah, to get from centimeters to meters, you just have to divide by 100. 251 something. Let me see. 5 Okay, Bishali, this time you're a bit off, but yeah, everyone else has the right answer. It's close to around 3.95 or 3.92, depending on how you calculated it, but yeah, that's correct, because right here, we can just directly plug in all the numbers and we would see that you get 3.9478, which you could round to 3.95. Yeah, this time you guys all got it, pretty much all got it correct, because turn centimeters to meters. Good job. Okay, that is it for today. Thank you all for coming. And here's our feedback form. Can someone put in the chat? And yeah, please fill in this form and give us some feedback. Yeah, once you guys fill in that form, feel free to leave. And yeah, what's your request, Michelle?